All right, happy National Spouses Day. Yeah, Spouses Day. Now I'm wondering if that is singular possessive, but I wonder if the plural would be not spouse but spice, right? Spice. Yeah. Okay. Anyway, your warm-up today is to integrate your favorite Leonardo DiCaprio film into your least favorite Disney animated film. Well, so your least favorite. So like Leonardo starring in The Jungle Book as Mowgli. There you go, as Mowgli. Ah, there you go. Cinderella's Castle is Shutter Island. Nice, nice. Yeah. How about okay, sure. Daffy Duck? That's Warner Brothers. Okay, we can do that. It's just a make-believe warm-up anyway. And Daffy Duck is just a duck in the cameo. Nice. Yeah, and Donald's like getting all angry because he's not in it. Okay, cool. All right, let's go to the notes then. The fundamental theorem of calculus. We're starting for real. Example 8. I don't think we finished it in here, did we? We were learning the second part of the FTOC, the fundamental theorem of calculus, and it was the part that said that the derivative of the integral just kind of undoes itself, right? And so what we were doing here is kind of showing why that works. So on example 8, we had the definite integral from 3 to x of this quadratic, and we found the antiderivative, and it was this here, and then when we evaluated from 3 to x, we ended up with a cubic polynomial, and now we are going to turn around and undo what we did yesterday. We're going to actually take the derivative of it. So let's do that. We get f prime of x equals. The first term becomes x squared. The second term becomes x. The third term becomes 1. And what happens with the derivative of this last constant that we didn't simplify? It becomes 0. So notice we're left with x squared plus x plus 1. And if you recall from yesterday, that looks very, very, very similar to our original, what do we call that? The integrand. Yeah, it looks very similar to the original integrand. The only difference is it's now a function of x instead of a function of t, which makes sense because, remember, it is big F of x to begin with. T is just some temporary variable so that we don't forget what our independent variable is. It's that upper limit of integration. So, is that reasonable to think that the derivative of the integral is just the integrand? Sure. You start with something, you integrate it, and then you turn around and differentiate it. How are integrals and derivatives related? They're inverses. Yeah, so they'll undo each other. So, yeah, there you go. So, if it works for that, I guess it must work in general, right? So here we could say the derivative then, with respect to x, of some integral from any constant that's in the domain of the function, call it a, to x of some function f of t dt, guess what it should equal? F of x. Good. It should become f of x. It's your original integrand, but it's a function of x. And we saw why it became a function of x, right? It was when we plugged in. When we evaluated using the first part of the fundamental theorem, it became a function of x. So that gives us a way then, if we are ever taking the derivative of the integral, to actually get to the answer without actually really doing any calculus, right? We don't have to do it this way. We don't have to integrate first and then take the derivative, which is going to be nice because it does save time. And the other nice thing about it is it doesn't require us to actually find the antiderivative, does it? You think the antiderivative is always going to be found or easily found or willingly found? No. And so if we're ever taking the derivative of the integral, that'd be nice. Okay, so let's summarize that. It's called the fundamental theorem of calculus part 2. Here's what it says. If a function is continuous on a closed interval, all right, just like the IVT and EVT, and if we define big F of x to be the integral from a to x of f of t dt, then the derivative of the integral from that constant to that x is just going to be f of x. It's going to be your integrand as a function of x. So it is required to go from a constant to x. And this constant has to be in the domain of f of t. Okay, you ready to try it out? I'm ready to try it out. Example 9a. The derivative with respect to x of the integral from 1 to x of secant of t. Any ideas? Secant of x. Perfect. That's the answer. Perfect. Because we're taking the derivative of the integral and we're going from a plain old number to a plain old x. It's just going to be the plain old integrand with x in there instead of t. Now, this is one that eventually we could, if we wanted to do it the long way, we could actually find the antiderivative, evaluate it from 1 to x, and turn around and take the derivative, and guess what we'll get? We'll get secant of x. But we don't know the antiderivative of secant yet, do we? We'll learn it soon enough. Okay, so right now, this is nice because it doesn't require us to know the antiderivative. All right, next one. The derivative with respect to x of the integral from plain old 5 to plain old x of the square root of p cubed sine of p dp. Does it matter now that it's with respect to p instead of t there? No. As long as that variable is something other than this variable here, in most cases it's x, you're okay. We're going from a plain old number to that plain old variable there. That's the same as this one. It should just be what? Times sine of x. Yeah. Do we need a plus c? No, because the last thing we're doing, if you look at the sequence of operations, the last thing we're doing is taking the derivative. Okay, we're taking the integral, then we're taking the derivative. The plus c would go away. So you're just left with the integrand. Okay, the next one, the integral with this, or the derivative with respect to x of the integral from pi to x of e to the k blah 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 dk. Don't think too hard. It should just be e to the x square root of x plus x squared all over natural log of x. Sweet. Now, the previous two that we just did, b and c, you're not even going to be able to verify those if you wanted to by doing the sequence, integrating and then evaluating and then taking the derivative, because the antiderivatives of these two dudes are very, very difficult, if not impossible to find. But we can still get our answer because we understand what's going on here, the derivative of the integral. Now, here's one thing that you want to be very cautious of. You get in the habit of just writing down the integrand, and you have to remember when it works. Because if I just asked you to take the integral from pi to x, like that, with respect to k, is that just going to be the answer? E to the x square root of x plus x squared, is it? No. Okay, it only works when we're taking the derivative of the integral. In this case, you would have to actually try to find the antiderivative and evaluate it, or maybe these are both numbers and it's a calculator question, okay? So it only works when it's the derivative of the integral. So don't get overconfident. All right, here's a bonus problem. If big F of x is equal to the integral from x to 3 of the square root of m squared times sine of m dm. Find big F prime of x. All right, is that a fundamental theorem part 2 question? How do you know? Yeah, the integrand is the thing we're taking the integral of. The whole thing is called the integral. So yeah, you said it. We're taking the derivative of an integral function. We're taking the derivative of an integral function. It's just not in the noun format. This is the verb format, the ddx. This is the noun format. So it's just another way to do it. We're defining a function to be an integral, and we want its derivative. Is it just going to be the square root of x squared times sine of x? No, why not? Why? The x is on the bottom. So the pattern works only if it's going from a constant on the bottom to an x on the top. And this is not that pattern, but we have a way to make it fit the pattern, right? We have a real quick way. If you flip the intervals of integration, all you got to do is stick a what out front? A negative. So as Iris said, Iris, you're on YouTube now. We have a negative in front. And you don't even have to show the step if you can do it in your head. So yeah, we have ways to make it fit the pattern if it doesn't. No big deal. All right, so far so good? Pretty easy? Yeah. If we quiz over this right now, hundreds, right? Pretty easy? Yeah, maybe not right now. All right, so if you notice up here, this said special case. And it's a pretty easy special case. The special case is when you're going from a plain old number to a plain old x. As we already saw, in this case, we're not always going from a plain old number to a plain old x. We could be going from a plain old x to a plain old number, in which case we can make it fit the special case pretty easily. But sometimes you're going from something that's not plain at all, and it doesn't even have to be numbers. Okay, so here's the most general form. The derivative with respect to x, in general, of the integral from a function of x, call it h of x, to a different function of x, call it g of x, of some integrand f of t with respect to t. It's going to be that. Let me show you how to do it. You want to memorize the pattern, not the actual letters. It's still going to be some form of the integrand because we're still taking the derivative of the integral, so we don't have to anti-differentiate. It's still going to be some form of f of t, but notice what we're doing is we're first plugging in our g of x for t to get f of g of x. We're plugging in the top. And then times the derivative of what we just plugged in. It's the chain rule. Minus, just like in the fundamental theorem part 1, you plug in the top, minus you plug in the bottom now. H of x goes in there, so it's f of h of x, and then again times the derivative of what you just plugged in. So you don't have to find the antiderivative, because it's still going to be some form of the integrand. You're essentially plugging in the top, times the derivative of what you plugged in, minus plug in the bottom, times the derivative of what you plugged in. It works every time, including these times. Watch. This is a special case, so it's still worth noticing that it's a constant to x, it's going to be that. But if you use the general rule, here's what the general rule says. Plug in the top for your variables, so you're going to get the square root of x cubed times sine of x, and then times the derivative of what you plugged in. What's the derivative of x with respect to x? 1. Minus, you do the same thing on the bottom. You plug in your 5, and you get 5 cubed times sine of 5 times the derivative of 5, which is 0. Now, here's why it's the same. 0 times anything is 0. 1 times anything is itself. And you end up with the exact same thing. So it's a special case. It's a little bit faster if you recognize it, but it works every time. It even works in this one here, because notice instead of flipping them and putting a negative, when you plug in the number first times its derivative, it becomes 0. And then minus, you do the bottom, and you get 0 minus this, and the negative's taken care of. So you can use the general rule instead of the special case. But look at example 10. Example 10. Evaluate the following using the FTOC2. And then it says to verify by doing it the long way. Long way. Okay, I see what I was after there. It's an ah, not a u sound. A long way. How do you make sure that it's that sound and not the u? What does that little symbol do in English? I don't know. What do you put an umlaut on there? That's a smiley face now. Yeah. Hey, let's just do it, okay? Example A. The derivative with respect to x of the integral. The derivative of the integral. The derivative of the integral. Now you're thinking what? FTOC 2. They's going to undo each other. We're going from a plain old number to a... Yeah, not a plain old x, right? To a complicated function of x. And we can't just flip the intervals of integration to make it fit the special case. But do we need the special case really? Absolutely not, because we have the general case. So let's go ahead and do it. Using the shortcut rule, which is the FTOC2, we're going to plug in the top for any variable we have in our integrand. So we get secant squared of 2x cubed. And then times the derivative, not of what we created, but of what we plugged in, which would be 6x squared. Some people want to take then the derivative of secant squared of 2x cubed. That's going to be, no, it's just the derivative of what you plugged in. So you plug in the top, minus, you do the same thing in the bottom, right? Same thing in the bottom. Let's go with blue. You're going to plug in a 1, and you get secant squared of 1 times the derivative of 1, which is 0. So if you recognize that it's a constant on the bottom, you know its derivative is 0. You technically don't even have to plug it in. But it does simplify to 6x squared times secant squared of 2x cubed. Boom, and you're done. Now, it's not the integrand perfectly with an x in it, but it is still some form of the integrand. It's a secant squared function. Now, you're probably wondering why the general rule works. I will show you right now. All right. I thought she'd comment. Anyway, let's go ahead and do it the old-fashioned way. Let's earn it. If we're going to do it the old-fashioned way, that means actually working it out using the fundamental theorem part 1. So I have to evaluate the integral from 1 to 2x cubed of secant squared of t, which first requires me, remember, to find an antiderivative of secant squared. Oh, how are we going to do that? What is the antiderivative of secant squared? Tangent. Okay, it works. Now notice I have the d dx out front because it's still part of the problem. I haven't done it yet, so you got to bring everything along. And now no plus c needed because it's a definite integral. We'll evaluate it from 1 to 2x cubed. All right, so still have a d dx out there. We plug in the top and we get tangent of 2x cubed. Minus, we plug in the bottom, tangent of 1. So we're done with the inside part. We've evaluated the definite integral. Now we're going to turn around and undo what we just did. We're going to take the derivative. So here we go. We got 2 terms. That's 2 problems. Yay! The derivative of tangent of blob, secant squared of the blob, times the what rule? Chain rule. The derivative of the blob, which is 6x squared. I'm going to slide it in the front. You can put it in the back. And then minus the derivative of tangent of 1. What's tangent of 1? Some number, right? What's the derivative of some number? 0. And so it's gone. And we end up with this. And is that what we got up here? Yeah. So in this case, you have the option of doing it both ways. One way is shorter, and the other way is longer, I guess, comparatively. And they're both fun. But sometimes you can't do the second method. Because remember, the second method is an incumbent upon your ability to find the what of the integrand? Antiderivative. And you think it's always easy to find? No. You think it's always possible to find? No. You think it's always fun to find? Yeah, even if it doesn't exist. Yeah, there's a joy in the adventure, right? In the search for. But you're going to be given questions that deal with this where you're unable to find the antiderivative. And so it's going to be encouraging you to use this shortcut method, if you want to call it that, the second fundamental theorem of calculus, or the fundamental theorem of calculus part 2. All right. On your mark, get set, you go. Find it the shortcut way. You do it the shortcut way, I'm going to do it the long cut way, and we're going to compare answers. Okay? Man, y'all are fast. Y'all are fast. Y'all must have known a shortcut. Did y'all get this answer here? Yes? Exactly like that? Well, I mean, I got it. Equivalent to it. You got this one. Yeah, I see. Oh, and then you distributed. Oh, good for you. Okay, good. Yeah, so you did get this one. Yeah, nice. Okay, so yeah, you should get that. You're going the derivative of the integral. That's the second fundamental theorem. You're going from e to the x to 7. You have the option, if you want, of flipping it and going from 7 to e to the x and putting a negative out front. But do you really even need to do that anymore, or does the general pattern take care of that? It takes care of it. So if you wanted to do that, it's fine. But if not, just plug in your 7 first, get blah, 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 times the derivative of 7 would be what? 0. And then you get minus, so then you have a negative answer. And then you get e to the x squared. E to the x squared is the same as e to the 2x plus 5e to the x, and you're done. Times what? You're not done. Times e to the x. Yeah, so that's where this one might come in. You have the negative there, and you get this, and then when you multiply by the chain rule, this is the thing that students forget. So if this were like a multiple choice answer, you can imagine what answer choice A would be, right? It would be this without the e to the x there, because people forget the chain rule. But not y'all, right? Okay, so that is equivalent if you do it the long way. I'll show you the long way very quickly, because you don't always have the option, but it is more work. You're going to have to integrate to get a cubic. You plug in the top, you minus plug in the bottom. You have the burden of the notation as well. D dx still has to be there. You're going to get this ugly thing. When you take the derivative, it goes to 0. And you get an equivalent version without the e to the x factored in. So if you factor out the e to the x, of course, you get the version y'all got, or if you got the version you got and distributed, and you get the version I get. So there you go. We've done it twice both ways, so now you should have faith in the method, right? Yes. So example 11. I'm going to give you 1 minute to do example 11, and I will tell you, do not simplify. Do not simplify. Just answer the question and get on out of there. Oh, yeah. I'll give you more time because you're writing it down. Yeah. Oh, Aggie basketball. Is that where you're going? Yeah, you gonna play? No, I'm just gonna go to the game, support. There's one with dogs on it. Yeah, I think you could be a baller if you try. You got the height. He does, yeah. The height, but I want the skills. Yeah. Hey, those come in 2 times. Careful, not natural log of 3 dx. Just natural log of 3. Right? Yeah. Oh yeah, that's good. No, you're fine. You're so close. You're so close. You're so close. Yeah, you did it right. Look over here and see how you're close. Yeah, it's exponential. So what would be the derivative of e to the x itself? So 3 to the x would also be itself 3 to the x, but and you multiply. No, the natural log of the base. Yeah, the natural log of the base. Good. Don't forget the chain rule there. That one has a double chain rule. This one has a double chain rule. Double chain, longer chain. Better for dogs. Yeah, there it is. Yep. Double chain. Yeah, there you go. Double chain. Good. Double chain. Ooh, you plugged in the bottom first. Yeah, you plug this one in first. You got to do the other way around. Yeah, so switch the signs, negative, positive. Remember, you got to plug in the top minus plug in the bottom. We read it from low to high, but you got to plug in the top minus plug in the bottom. It's like finding a distance. Top minus bottom. Don't forget the chain rule there. There's another chain rule. The 3 to the x is exponential. So like e to the x, it's its own derivative. So it would be 3 to the x, but because it's not base e, you multiply by the natural log of 3. So it would be 3 to the x times 3. Good, double chain rule. Good. Yeah, so this one is big F, and it's the integral from funky function to funky function, right? Neither one of them are constants, but our integrand is the natural log of t. Now, later on, we would have the option of doing this one the long way because you'll memorize or you'll be able to figure out the integral of the natural log using integration by parts. But even once we know how to do it the long way, we would still prefer to do it the way we're about to, right? We're trying to find f prime, so that's the derivative of the integral. That's FTOC2. So we plug in the top. Always plug in the top first. And then times the derivative of what we plugged in. The derivative of 3 to the x is 3 to the x times the natural log of 3. These questions are wonderful opportunities for me to quiz you and review you on your derivative rules. Nice. So you plug in the top and then minus, you do the same thing on the bottom. Ooh, the natural log of parentheses, 2 plus sine of 2x. And then times the derivative of 2 plus sine of 2x, which I saw a lot of you are writing the 0. That's good for accounting purposes. Plus You don't have to write that for a check. If it's missing, we know, well, we'll assume that you knew that it was 0. The derivative of sine of blob is cosine of blob. But then you have another chain rule right there times 2. So that's how you would write it if you put the 0 there. If you didn't have the 0 there, then of course you could put it in its own parenthesis. And that's it. You could walk away from there. If you feel like simplifying it, you can do that. All right. You want me to quickly show you the natural log's derivative or antiderivative? Just kind of a preview of coming attractions because we have some little bonus time right here before lunch. If you have to find the antiderivative of the natural log of x with respect to x, here's what you're going to do. You're going to let u equal the natural log of x. It's kind of like u substitution. And you're going to replace dx with dv. What's dv? Well, it's the derivative of v. Now, on the left column, you're going to take the derivative of u, and the derivative of this becomes 1 over x dx. So that's called the differential form of the derivative. Instead of du dx and then multiplying both sides by dx, you go straight to du equals 1 over x dx. And over here, you're going to integrate both sides. The antiderivative of v is, or dv is v. The antiderivative of dx is x. Yeah, v is, this is called uv substitution instead of just u. Now, if you've ever seen Zorro, right? Zorro makes his z. That's how you know Zorro was there. But then there's dyslexic Zorro, who's like, and that's how you know dyslexic Zorro is there. He makes the z backwards. So here's what you would do. This first arrow back here restates the problem. It's the integral of the natural log of x with respect to x. The first diagonal then becomes a product. So that equals x times the natural log of x. And then this last line in the z becomes minus, always minus the integral of the product, x times 1 over x dx. Oh, absolutely. This is just a little preview of coming attractions. Now, if you integrate this, you could simplify first. What's x times 1 over x? 1. And what's the antiderivative of 1? X. The antiderivative of 1 is x. So you get minus x, and then, of course, plus c. And so there it is. There is the derivative, or the antiderivative of the natural log of x. Let's check it. Let's check it. How do you know that's right? You just trust me? I wish my wife did. That's a joke. All right. Now, let's check it real quickly with the product rule. We get 1 times the natural log of x plus x times the derivative of the natural log of x, which is 1 over x. And then minus the derivative of x is 1, and c goes to 0. If you simplify, you get the natural log of x plus x over x is 1 minus 1, you get, yeah, there it is. So this is called integration by parts, and it's one of 2 ways we're going to learn it. This is what I call the backward Zorro method, which is less pejorative than dyslexic. And then there's also a tabular method, which I call tic-tac-toe method. So anyway, you will be able to do this using the long cut method later on. But even though you know the antiderivative is x ln of x minus x, you don't want to have to do this problem that way. There you go. A bonus little lesson inside here. That's a BC only topic. Have a fantastic lunch.